Hello everyone. This is part one for variation of parameters. Basically today we're going to see the theory behind the development of our formula, which if you scroll down a little bit under the theorem you see a kind of complicated solution for y sub p. So we're going to look at how that comes about. And for this there is a document called Variation of Parameters Theory located in the handout folder above the where the videos are. So you might want to print that or just follow along. It's pretty complicated and you're not going to be held responsible for the theory, but I feel it's important to at least be exposed to it so that you see where things come from. So I'm not just giving you a formula and you're just plugging into it. So the whole idea of method of undetermined coefficients is that we're able to pick functions that could be solutions to the particular solution because they have a finite combination of linearly independent derivatives. In other words, the main classes of functions that we looked at, if you look back at our examples, were exponentials, sines and cosines, and don't forget, of course, polynomials. Those are the ones that worked well for. But if you have a function like tangent of x, if you start taking derivatives of tangent, you get secant squared, and then after that you get something more complicated, and there's an infinite number of linearly independent derivatives. So this is the function, one of the types of functions that's causing undetermined coefficients to fail. So as I said earlier when we started this, see the handout posted, and we're going to develop the theorem for variation of parameters. You might want to print that and follow along and fill in all the details. But part of what we're going to do in the derivation of a formula is use Cramer's rule to solve a system of equations. Now, if you've never seen Cramer's rule before, it's used to solve a system of, can be used to solve a system of two equations and in two unknowns, as I have set up here. Here's the easiest way to go about it. I'm going to call this D for denominator, and you basically just take the coefficients of the x and y variables when they're set up in this fashion, where you have x's and y's on one side and the constant terms on the other. So you just peel off their coefficients, 3, 2, 2, and 3. And then that's our 2 by 2 determinant, so we get 9 minus 4, or 5. Then I'm going to call this next one n sub x, meaning the numerator of the x variable, of the solution to the x variable. And what we do is we set up another 2 by 2 determinant, but we replace the x column by the solutions. Okay, so 13, 12 replaces 3 and 2. And then we just recopy the y's. Okay, so crunching that out, we get 39 minus 24, or 15. And let's do the same thing for what I'm going to call n sub y. But now we're going to keep the x's, 3 and 2, and replace the y's by the 13 and the 12. And that gives us 36 minus 26, or 10. So the solutions to this system are that x is going to be n sub x over d, so 15 over 5, or 3, and y is going to be n sub y over d, and that's 10 over 5, or 2. Okay, so kind of a nice little method. If you haven't seen it before, might be something you want to consider putting in your repertoire. So there's the theorem, and we're going to go to the page I mentioned that's in the handouts, the variation of parameters theory page. And we're going to show how this formula is derived. So this is a general method for solving any non-homogeneous second-order differential equation. And what's causing it to be non-homogeneous, of course, is the fact that it's equal to some function of x. We can look at the associated homogeneous, and what's making it homogeneous is the fact that we're setting it to 0. And we suppose that y1 and y2 are linearly independent solutions of the homogeneous. So if these have constant coefficients, we can find y1 and y2 very easily by our theorems that we've been using all along. And so it follows that general solutions to that homogeneous is going to be of this form. Y sub c is c1 y1 plus c2 y2. And you could use the functional notation if you want, but when we get to calculating some derivatives, we're going to drop it. Okay, so now what we do is we replace the constants c1 and c2 by the actual functions u1 and u2. So u1 replaces c1 and u2 replaces c2. So that what we have now is that y sub, and we assume that by replacing those by functions, we're going to be able to find those two functions to get the particular solution. So we replace c1 by u1, c2 by u2. Again, now we'll drop the functional notation, and we assume it satisfies the non-homogeneous differential equation. So if it does, well, we'll take a couple derivatives. And so here's the first factor, u1, derivative of the second, y1 prime, plus second factor, y1 times derivative of the first, and that's u1 prime. And then here, if you like, it's another product rule on u2, y2 to give us this. And then what we did was we regrouped things. We chose to group the u1 prime and the u2 prime together, and then having the u1 and u2 as a separate entity in parentheses here. And then this step here, basically the reason why this is chosen is to avoid having second derivatives of u1 and u2. So we force this term, u1 prime y1 plus u2 prime y2, to be equal to 0. And notice that that is this term right here. So we impose that condition. So then y sub p prime becomes just this term, u1 y1 prime plus u2 y2 prime. And then we take the second derivative of that. And so by the product rule, first factor, derivative of the second, y double prime, plus second factor, y prime, derivative of the first, u sub 1 prime. Okay, again, the product rule on the second one to give a similar result. And then we make the substitution into the non-homogeneous differential equation. So the non-homogeneous was y double prime plus p y prime plus q y equaling f of x. So that was the non-homogeneous, because we're assuming y sub p is the solution to that. And so we have y double prime, so that's these first four terms, and then plus p times, here's y prime, and then plus q times, here's y, and that's equal to f of x. And then we regrouped this so that we gathered all the terms containing U1 together. So if you look at just the U1s, we got that guy, this guy, and this guy. Okay, so we factored out a U1. There's the Y1 double prime, there's the Y1 prime, and there's the Y1. And you see P is times Y1 prime and Q is times Y1. So then we did the same thing with the U2s. Just the U2s, not the primes. And so we've got factoring out the U2, Y sub 2 double prime, is P distributed times Y sub 2 prime, and then plus this Q distributed times Y sub 2, after factoring the U sub 2. And then the only terms left over are these two guys, and we just listed them here. And that's equal to f of x. Now the significance of that is the fact that if you look up at the associated homogeneous equation, so that's way at the top here, y double prime plus py prime plus qy is equal to 0. So let me rewrite that here. Y double prime plus py prime plus qy is 0. That's the homogeneous. And so therefore, it turns out that each of these terms equals 0. And so we're left with this. Just this quantity equals f of x. Alright, so we're going to hold on to that for a minute. And if we take the two things that we've boxed off at this point, could call this Roman numeral 1 maybe, and this Roman numeral 2. And if we solve that system for U1 prime and U2 prime, this is what we get. And let me show you quickly. I'm going to go to I kind of skipped some steps there. I didn't show it literally, but let me show you quickly how, using Cramer's rule, I'm grabbing another sheet of paper here. Again, you're not responsible for this, but it's kind of really cool if you understand the procedure. Okay, so we're going to solve this system U1 prime Y1 plus U2 prime Y2 equaling 0, and U1 prime Y1 prime plus U2 prime Y2 prime equaling f of x. Okay, so what we're going to do is solve for U1 prime and U2 prime by Cramer's rule. So the denominator is going to be U1 prime and U2 prime are behaving like the x's and the y's in our Cramer rule example. So we have Y1, Y1 prime, Y2, Y2 prime, and you can calculate that out if you like, but note that this is actually the Wronskian of Y1 and Y2. So that's interesting. And then if you want the numerator of x, remember we replace the x column by the solutions. So 0, f of x, and we leave the y's, y2, y2 prime. And so this gives us 0 minus f of x times y2. I'll write it as y2 f of x. So minus y2 f of x for the numerator of x. Or actually, you know what, to be even more efficient, call this the numerator of u1 prime, because that's what it is. And then similarly, we'll say the numerator of u2 prime would be, okay, now we leave the first column alone, y1, y1 prime, and the second column replaced by the 0 and the f of x gives y1 f of x minus 0, or just y1 f of x. Okay, and so then we get that u1 prime is the numerator minus y2 f of x over the Wronskian of y1, y2, that was the denominator, and that u2 prime is y1 f of x over the Wronskian of y1 and y2 again. Okay, and so if we look at where we were at, that's exactly what we have. At that point, I use functional notation for the y1s and y2s here, but you can see it's the same thing. Remember the Wronskian, what that is, you can calculate its determinant. So, pretty interesting, kind of cool. And then if we integrate that and substitute into, so we integrate each of these to get u1 and u2 respectively. So you basically just, u1 prime is going to be the integral of this, or u1 is going to be the integral of u1 prime, u2 is going to be the integral of u2 prime, and then you substitute those into y sub p. That gives us the particular solution. And so then we have the formal theorem stated. Okay, so and we factored out the minus y1 and the y2 from our integrations. Okay, so that's the theory, and I think I'm going to cut it short there. We're basically at the point where we can start talking about this example, because there's the theorem again, and we're going to look at two examples. So we'll come back and I'll finish up this. This is part one of variation of parameters, and we just have two nice examples, so that'll be part two, and we'll be done with this topic, and we'll move on to an application of RLC circuits. So we'll see you next time.